So last week we finished until this part. We learned about the measures for the decision tree and how we split the continuous values and then how we split the discrete values. So as I mentioned to you, I updated the PowerPoint. In this slide, we want to learn about overfitting. What is the meaning by overfitting? Fit. Fit means enough, okay? Just enough or just proper. If we call it overfit, it means it is more than enough. Or because this overfitting, an industry may overfit the training data. It means there are too many branches. So like this one, this is one example of decision tree. There are too many branches and some may reflect anomalies because there may be noise, outliers. And it will be poor accuracy for unseen samples. For example, this one. You know pet. Do you want to buy this kind of pet? Of course, you will not buy because this pet is very specific. Yeah. Because this is overfitting. Because the pet is not for the general people. The pet is very specialized only for this person. When we want to make the model in the data mining, in the artificial intelligence, in the machine learning, of course, we want to make a good model where many people can use it. The same with this idea. We want to make a pet where many people can use the pet. So we need to avoid, because this is the overfitting. So how to avoid overfitting? There are at least two approaches that I want to teach you here. Yeah. The first, we call it the pruning techniques. Do you know prune? Prune means we want to cut. Two approaches. The first is pre-pruning. Pre-pruning, so we want to cut before because we want to call it pre. Okay. Pre means before. So before we construct the tree, we hold the tree construction early. So before we construct the decision tree, do not split a node if this would result in the goodness measure failing below a threshold. So if we already set a threshold, and let's say the tree is below the threshold, then we cut before we build the decision tree. This is difficult because we need to choose an appropriate threshold. This is the most difficult part because maybe we need to tune single parameter or we need to tune multiple hyperparameters. The other approach, we call it post pruning. Post. Post means after. After we have the decision tree, we want to remove branches from a fully grown tree. So it means a complete tree, and then get a sequence of progressively prune trees. So we will step by step. one by one cutting the branches. We can use a set of data different from the training data to decide which is the best prune tree. It mentioned here, it requires more computation than pre-pruning, but lead to a more reliable tree. So the post-pruning, it is cost complexity pruning. So the algorithm will learn and learn and learn, so the complexity will be higher. This post-pruning is higher than pre-pruning. So it depends on what we want to achieve. However, it mentioned that it leads to a more reliable tree. So using the post pruning, it will give you a more or a better tree. The other technique is creating ensembles, but I think I will not discuss in detail. So let's just learn these two. We have this decision tree. So let's suppose I have this decision tree and okay, I want to prune. Okay, so this is unpruned decision tree. So if I prune, you can see that the decision tree is more easy to understand. It is easy to interpret rather than the full prune tree, because this is the full prune tree or the complete tree. Okay. So the fully grown tree, as I'm looking to here, fully grown tree. How we can cut? The question is how we can cut the tree. First, we can see any repetition. What is repetition? Let's say I have this one, A1. Let's suppose A1 means the age. Okay. The person age is very diverse. Maybe from the age 0 until the age 100. So the data we have are diverse, and based on the result, the most important attribute is age. And then there is a splitting point. It mentioned 60 as the splitting point. So we split into yes and no. And the next stage, when we calculate, it comes that the next important attribute is again age. And the splitting point now become 45. And then again, when we check the next split, the next attribute that is most important is age. And the splitting point now is 50. So age is repeated for 3 times. 1, 2, 3. Then we call this is the sub-tree repetition. Even though the splitting point is different, but the attribute is always the same. So where an attribute is repeatedly tested along a given branch of the tree, okay, for example, age. There is another kind of possible subtree. We call it replication. For example, now we have x equal to u. If it is yes, then okay, we will check the attribute student. If it is yes, then it is the class B. But if it is no, okay, we have the attribute credit rating. So we will have this tree, okay, and I make a box here. This box, with this box, they are the same. But it is from the attribute age, and this is from the attribute student. Okay. Even though they are from different branches, but they are the same subtree. So we call this is subtree replication. It is where the duplicate subtrees exist within a tree, and the subtree headed by the node credit rating. Okay, so this is the head. This is the head. So what can we do with this one? This kind of possible subtree, we call the subtree repetition and subtree replication. We can use it for cutting down the branches. So subtree repetition and subtree replication can impede the accuracy and the comprehensibility of a decision tree. The enhancement of basic decision tree, the enhancement is the improvement. The improvement of the decision tree, we can allow for continuous value attribute. So what we learned until now, most of the data are from the categorical data. The categorical attributes, we use it to determine the categorical target. So if you allow this the continuous value, so it means, with the measures like maybe the Gini index, you can dynamically define the new discrete value attributes that partition the continuous attribute value into a discrete set of intervals. We can improve the decision tree by handling the missing attribute values. So we learn about the data preprocessing about these missing attribute values. For example, if it is categorical, we can assign the most common value of the attributes. Or we can check the probability. So we will assign probability to each of the possible values to handle the missing attribute values. We can also make a new attribute, or we can construct attribute. Create new attributes based on existing ones that are sparsely represented. You know, what does it mean by sparse? Sparse means when your data contain a lot of zero or not exist data. If you still remember, when we learn association rule, the data will be something like this one. Bread. If the person won buy bread, it is 1. If the person didn't buy bread, it is 0. Okay. What about the other product? Maybe I have milk. Okay. Or maybe I have another product, almond. Not many people would like to buy almond. So maybe when we have 1 million data, it will be like 0, 0, 0, 0, 0, 0, 0. Only one person will buy it. So we call this is sparse. There are many zeros. Or you can have a lot of products. Maybe let's say water. So water, you know, in the supermarket we have several sizes. Water 2 liter, water 1 liter, water 500 milliliter, water 300 milliliters. If people just bought the water 2 liters, it is one. Okay, there are many one. But maybe the small water, there are not so many people who buy. There will be zero. So this kind of things, yeah, we call it sparse. If the data is not available for many observations, maybe we need to create a new attribute to make the decision tree in a better result. So this reduces the fragmentation. It will reduce repetition. It will reduce replication. So if we do with the classification in the large database, it means, yeah, we want to check if the classification can be with the big data. Classification is a classical problem extensively studied by statisticians and machine learning researchers. The issue will be the scalability. The scalability means how we can classify a data set with millions of examples. So it means if we have a lot of rows and hundreds of attributes, it means we have a lot of columns. So how we can classify our data with very big data with reasonable speed? Okay, so the decision tree, the decision tree induction in data mining, it is faster than other classification methods. So that's why we learn the basic one is the decision tree induction. It is comfortable to simple and easy to understand. So when you have the tree, you will have node, and the node is representing the attribute. Let's say, okay, this is the attribute age. Then I understand that this is the most important attribute for the decision tree. And then I will make the next. The next attribute, maybe this is student. Okay, this will be the next possible condition to make a good decision. So the easy to understand, and it is simple for the classification rules because it has the interpretability. Okay, we can interpret it. We can use SQL queries for accessing the database. So once we have this result, we can access the database and then we can just follow the condition. If age is less than 30, yeah, what happens? If age is greater than 30, yeah, we can just make the query. And yeah, comparable classification accuracy with other methods. It means the result for the classification with decision tree is still good enough. Even though maybe it's not the best, but it is still okay. So if you learn about the algorithm, you will see this kind of graph. So the decision tree induction, it is an algorithm with a reasonable response time. So the response time means if the number of data is bigger, what is the execution time? If your algorithm is O1, yeah, of course it is good. Because the higher data, the higher number of the data, the time is still always the same. But if we have the O2N, like this one, the higher the number of the data item, the response times is getting very high. we do not want to use this algorithm. So we want to use this algorithm, or maybe this algorithm, or maybe this algorithm. So the decision tree is still in the open. So that's why it is faster than the other algorithm, which is maybe 2 power of n, or maybe this algorithm, this algorithm, this algorithm. This for algorithm is taking more times or a lot of time for giving the response. So there are many other scalable decision tree induction methods. Yeah, if you want to learn, yeah, you can check on this. Okay, I will skip this one. Now, when we have the model, we need to check the model. You still remember in the classification, we have two processes. The first is model construction. The model construction means we use the data and we split it into training set and the testing set. We use this training set data to create the model or to construct the model. What we learned until now is, we want to get the model, which is the decision tree. After we have this decision tree, we want to estimate the accuracy. So we go to the second part, which is the model usage. Okay, so you learn in the first part of our slide, there are two processes of the classification: model construction and model usage. Or in this part, I call it evaluation. So we can also say this is the model evaluation. The first is model generated using the training data set, and then model is evaluated using a test data set. I put numbers here. Usually, people will split on the percentage. 60 training set, 40 test set. It means 60% from the data, it will be the training set. And 40% of the data, or the remaining of the data, will be the test set. Or sometimes people also use 70-30, 80-20, or 90-10. It depends on the number of your data. If you have a lot of data, maybe you can use 90 and 10. Because let's say you have 1 million data. You have 1 million row. If you have 1 million row, it means 90% of this data, this is 900,000, okay, it is for the training set, and then the other 100K is for the testing set. So if you have a very huge data, then 90-10, you can use it. But if your data is very small, let's say 100 data, then usually we use the 60-40. The smaller it will represent better. Or if you want to use this one, 80-20, that's also possible. So we have 80 data for training and we have 20 data for testing. So let's say in the data that we learned before about the bias computer, if you still remember, we have 14 data. Okay. So among the 14 data, I would like to split it into the training data which is the 70%. So you can calculate 70% multiplied by 14. Maybe about 10 point something, 10 comma something something. So you can just make it 10. So this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. From this training data, I would like to make the decision tree. And after I have this decision tree, I would like to test this decision tree into this testing data. So the testing data is the remaining, which is the 30%. So the 30% is like maybe 3 point something something. So we round it into 4. So we have 4 data, 1, 2, 3, 4 for testing. We have the information, or we call it this actual data. The actual means, yeah, I know in this testing data, this person, he didn't buy a computer. This person, he bought computer. This person, he bought computer. This person, he bought computer. So this is the actual data. And now I'm going to use this decision tree. Can I use decision tree to predict? To predict the result. So let's see from the data. First, the most important attribute is age. Then I would like to check from the age. What is the age? It is less than equal to 30. Then it goes here because the condition is less than or equal to 30 or higher than 40. Now I need to check income. What is income? Income here. What is it? Okay, we have medium. Then we have this side because it shows two conditions, low or medium. And then we have age. Next, age. Again, we need to check this one. The age is less than equal to 30. Okay, we go here and the decision is yes. So we put this decision into the predicted result. Actual is no, but the prediction result from the model or from the decision tree, we got yes. Now let's see the second example. 31 until 40. So the age 31 until 40. Okay, it goes directly to the decision yes. So this one is yes. What about next? Higher than 40. Age is higher than 40. Okay, we go to this side. And then let's check the income. Okay, the income is low. The income is low. Okay. And then check again the age. The age is higher than 40. Higher than 40, then the result is no. So we put no as the predicted result. And the last one, yeah, we also have the same. Okay, 40, higher than 40, and then this is medium. So the result is no. Because we have this no and yes, now we can make this matrix. How many actual and how many predicted that we have? If the actual is yes, how many of them if the predicted is yes? Okay, we have actual is yes and the predicted is yes. Okay, we have one. So we call this is 1. The actual is yes, and the predicted is no. The actual is yes, and the predicted is no. So we have 2. The actual is no, and the predicted is yes. The actual is no, the predicted is yes. We have 1. And actual is no, predicted is no, is 0. We don't have any data. What is not? So we call this is the confusion matrix. Okay. With this confusion matrix, we can measure the goodness of the model. Okay, we call this confusion matrix. It is useful tool for analyzing how well the classifier can recognize tuples of different classes. We have the actual class. Yeah, at this moment, we have yes and no. Okay, we have yes and no for the predicted class. We call it TP. What is TP? TP is the true positive. We have TN. TN, we call this is true negative. We have FP. FP, we call this is false positive. We have FN. FN, we call this is false negative. We have P, we call it as positive, and we have N, we call it as the negative samples. Okay. So for example, I have many data. Let's say I have like 10,000 data. So among the 10,000 data, I got this confusion matrix. So the same with the previous one, we learned from the small examples. Now we have a lot of data. We have the actual is yes, and the predicted is yes. And the number is 9,000 something. The predicted is yes, and the biocomputer is no. So we got 46. We have the biocomputer is no, but the predicted result is yes. Okay, we have this. If it is no and no, okay, we have this. Okay. Now we can see that there are, from my data, we have 7,000 people who bought the computer, and I have 3,000 people who did not buy computer. So we can calculate the recognition. What is this recognition? So this recognition means the accuracy. We want to know if our model can predict correctly. So we call this is the accuracy, and we can get it from the 6,954 plus 2,588 divided by 10,000. And with this formula, we will get this value. So let's get back to the previous one. We have this result. Okay. Now, I want to know what is the recognition rate, or what is the accuracy. You can check the number of yes and yes is 1, and the number of no and no is 0. So the 1 plus 0, and then we want to divide with the number of data that we have in the testing. So we have 4. Okay. Then what is the recognition rate? It is 25%. So it is very low. So the formula will be something like this one. We can get the accuracy. The accuracy means the TP plus TN. TP plus TN divided by P plus N. Divided by P plus N. The error rate or the misclassification rate, we call it, this is the FP plus FN. FP, this is the false, plus FN, which is the false, divided by P plus N. Divided by P plus N. We call this is sensitivity or true positive rate, or recall. True positive rate. True positive rate means we have the true positive divided by the overall positive divided by P. We have the true negative rate or the specificity by this formula, Tn divided by N. Tn divided by N. Or we can have also the precision. We want to know the model, whether it is precise or not. So we can do with the TP divided by the TP plus FP. TP plus FP. Or we can do with the TP divided by P prime. P prime. This is the total. We can have another method, we call it F score or F1 score or F score like this. It is the harmonic mean of precision and recall. What is precision? Precision is from this formula. What is recall? Recall is from this formula. And we will divide with the precision plus recall. Okay. Okay. I just give you a hint that there will be one question about this in your exam. Okay. Please try to understand how to calculate the accuracy, the recall, the precision with this formula. So in overall or in the review, yeah, you can check this one. The sensitivity, it is this formula. The specificity, it is using this formula. The precision, we use this formula. And we have the negative predictive values. We have this formula. And the most important method, which is accuracy, we can use this formula. We call the false negative as the type 2 error, and we call the type false positive as the type 1 error. When we do with the prediction, we learn that in the classification, the target is categorical value. When we have the prediction, or sometimes we call it regression, or sometimes we can also mention as forecasting, the target is numerical value. Okay. If we have the categorical values, we can make the confusion matrix. But if we have the numerical values, in order to measure the predicted accuracy, we need to measure how far of the predicted value is from the actual known value. So the loss function, it will be the measures between the actual values yi and the predicted values, which is yi prime. So the absolute error means we will use the absolute function and then yi minus yi prime, or it is the predicted values. The square error means the yi minus yi prime power of 2. So we take the square to eliminate the negative. For the generalization, we can make the average. So we can sum from all the data and then we can divide with the number of data. This is the mean absolute error. Or we can have also mean square error. It means we can sum all the data and then divide with the number of the data. If we are dealing with the relative absolute error, it means we are dividing this absolute error, we do the summation, and then we divide it with the bias or the error with the average. Okay. This is the average, not the actual. If we are dealing with the relative square error, it means we will do the square and then do the summation and divide it by the bias with regard to the average. This is the average. So the mean square error exaggerates the presence of outliers. So it will make the outliers bigger and bigger. So that's why usually we will use the square root mean square error. It means we will make the square root to make it as the RMSE. It means the root. R means the root mean square error. So the last one that I want to mention to you is about this overfitting. So we learned about the overfitting before. The overfitting means we have the very low training error. We have very low training error, and the training error much lower than the test error. The testing error is high. The training error is low. Okay. You know, if we have the two data set, training and testing, so we can distinguish the error rate for the training data and the error rate of the testing data. If the error rate of the training data is low and the error rate for the testing data is high, this is okay. What about underfitting? Underfitting means the training error is high and the training error close to the testing error. So the testing error is also high. What we want to get is just right. How to get the right model? The training error slightly lower than the testing error. The training error should be lower and slightly lower than the testing error. So we got this is the just right model. So when you create the model in your team project, I guess you will have this thing. You need to find a good model. You need to find the right model. Okay, I think I will stop here due to the time. So yeah, your exam will be